Ladies and gentlemen, thank you for standing by. We had a bit of a technical glitch there. Our webinar for Do More with Data from Stantec is about to begin. I'd like to welcome Kim Hubbard, who will host our session. I will let you all know that you are on mute as the audience, and if you'd like to participate with questions, you're welcome to do so through the questions panel on your computer. With that, I'll hand it over to Kim.
Hi, welcome everyone, and thanks for taking the time to be here. This webinar is the second of 3 led by Stantec's Integrity Group. The first was the Threat Assessment for Pipeline Safety Assurance and can be found on stantec.com. And in Q1 of next year, look forward to hearing about maximizing equipment lifecycle. As mentioned by Jerry, questions are welcome throughout. We want this to be interactive for you, the audience. And in between topics, there's going to be 2 polls for you to participate in. I'm here with James Ferguson. James has selected a few of the topics among the so many digital initiatives that are happening here at Stantec in the digital and innovative areas. And later, James will provide a summary on each subject. As mentioned, I'm Kim Hubbard, the Digital Practice Leader for the Energy and Resources Business Operating Unit here at Stantec. Although we are living in trying times through a pandemic, slowdowns in many of our industries, we are also living in a very fast-paced digital time. Optimizing data through technology and improving efficiencies will echo throughout this webinar. Stantec's 2020 strategic plan includes innovation, along with people, growth, and excellence as our key values. Stantec's digital transformation through innovation and technology will add value, drive delivery effectiveness and shareholder value, and help us achieve digital efficiency, resiliency, and security, which will carry through to our clients and our projects. Today's agenda will cover a range of digital technologies, tools, and systems, starting with remote sensing in large area data gathering. The Bending Strain tool will cover analysis of data proactively identifying concerns or possibilities. We will then move into visualization through scanning and digital tools and the importance of virtually seeing our facilities or sites remotely. And last, we will focus in on material that can't be measured and stresses the importance of data being the truest asset. Before we dive in on today's presentations, I wanted to take a safety moment to talk about protecting data. Why is this a safety moment? Well, because we Stantec, you the audience, every company has data, whether it be drawings, design files, documentation for projects, GIS data, and so much more. We all have data. We gather data, invest in technology and tools, plus the staff to manage and protect all the data. Ensuring that companies are equipped to manage and keep this asset accessible for staff, clients, and consultants, whether the data resides on networks or in cloud hosting environments, keeping it safe is key. And now Grant Wiseman will discuss remote sensing for threat identification.
Hello, my name is Grant Wiseman, based in Winnipeg, Manitoba. I am a remote sensing scientist, and I am the technical leader of Stantec's Remote Sensing Center of Excellence. I'm excited to tell you today about a new product we are calling PipeWatch. PipeWatch uses state-of-the-art Dove satellite imagery that is more cost-effective than traditional piloted air surveys. The challenge that many of you face is how do you cost effectively monitor these massive networks for integrity? Challenges that you face are release events, third-party encroachment, and theft detection in developing countries. There has been a technological advancement in the world of remote sensing, particularly Dove's satellite imagery. Pipewatch uses high-resolution satellite imagery collected daily, allowing for hundreds or thousands of kilometers of pipeline network to be inspected regularly. So you may be asking how Dove satellite imagery works. Well, Dove satellites are very small in comparison to traditional satellites. That means they're very inexpensive to build and inexpensive to launch. So companies have been launching them by the hundreds. Working as a team in a constellation, these Dove satellites travel from the North Pole to the South Pole in single file, collecting imagery as the Earth spins on its axis. These Dove satellites are collecting 4 channels. They're collecting the red, green, and blue, and the near-infrared channel. And that's really critical because that near-infrared channel gives us highly sensitive information on vegetation that resides on pipeline right-of-ways. Another innovation that these Dove satellites are providing is everything that they're collecting is being archived. Unlike traditional satellites, they would only collect imagery when they have a paying client, whereas these Dove satellites are collecting 24/7. So we are living in unprecedented times. These Dove satellites are collecting a record of the entire Earth's surface each and every day. Through careful examination of the vegetation photosynthesis absorption and reflection rates, Pipewatch generates highly sensitive health signature images of pipeline vegetation. Pipewatch automatically performs veg detection, health change detection analysis, searching for drops in vegetation health due to a release event, third-party encroachment, or theft. We are effectively using the vegetation as a surrogate measure of the ground disturbance event. In this example, we see the 2 vegetation health signatures on the left, date A and date B. Anything in green represents healthy vegetation. Anything in red represents stressed vegetation. When we perform our change detection analysis, we see that there is a sudden drop in vegetation health. This would signify that there has been some sort of ground disturbance event at this site. In this example, Pipewatch successfully detected this release event 5 days prior to the company's knowledge. We can also detect subsurface leaks. Here we're looking at a cross-section of a typical pipeline. There may be a small pinhole-sized leak that isn't detected by pressure sensors. This accidental release will have contaminants leaching up into the fill of the pipeline right-of-way. Eventually, it will work its way up to the roots of surface vegetation. When the vegetation ingests that contaminant, this will cause stress, and our highly sensitive vegetation indices will pick this up. Using change detection analysis, we will discover this change in vegetation health from 1 day to the next or 1 week to the next. So Pipewatch is effectively acting as an early detection system. It has several advantages over piloted aerial surveys. We're using the near-infrared channel that is invisible to the human eye. We are using quantitative statistics to continuously compare against what happened the day before or the week before. Piloted aircraft do not have this luxury. Not only can they not see the stress on vegetation, they have nothing to compare it to. As I mentioned, we can detect both surface and subsurface releases, and we are more cost effective than traditional aerial surveys. We have done several studies now where Pipewatch costs have come in less than traditional aerial surveys. And with that, I'd like to turn it over to the next presenter. Thank you for your time.
Fantastic info, Grant. And I think it's really important to note that beyond satellites, Stantec is using many technologies, including drones, to assist in remote data collection. Following threat management, we move from identification to assessment. And though these topics may seem similar, Kelly's analytic tool topic is very unique and so important to our industry. Kelly.
Hey, thank you for Kim. Thank you, Kim, for introducing my topic. Now I'd like to spend a few minutes to talk about pipeline threats, how to identify those threats, and the tool that can facilitate the process of threat assessment. Hey, Jerry. Okay. The pipeline threats we are focusing on today are related to ground movements causing pipeline damage and breaking. Ground movements such as landslides and settlement. Hydrotechnical movements such as shifting or increasing water flow can pose serious threats to the integrity of pipeline. The consequence of a ground movement event can vary greatly. Certain types of ground movements are gradual and can be monitored and mitigated before a catastrophic failure occurs. However, other forms of ground movements can occur instantaneously and can be very difficult to predict. The technology of bending stream data analysis has been successfully used to detect landslide interactions for decades. The identification of pipeline hazards related to ground movement has been a key part of any integrity management program where the pipelines have experienced abnormal streams during construction, maintenance, third-party interaction, or outside geo and hydro forces. Traditionally, the LI-MU data has had to be manually correlated with geo and hydrotechnical data and any other pipeline-related data, such as previous integrity-related excavation. There's a luminous amount of data across multiple data sources. It's very common to see that multiple inertial datasets don't line up properly. So when you look at the plots on the screen, you may ask, can those inertial datasets be automatically adjusted to align each other? Something like this. Other question you may have are, where are the girth wells located on the plots? Is that specified pipeline segment within geohydro location or past dig site? Another question you may ask, are there any defects or anomalies reported in this area? So with those concerns in mind, how to aggregate and visualize the data in a reliable, accurate, efficient manner is critical. The automated analysis tool Stantec has created allows overlaying various LI-MU datasets of interest corrected for log distance misalignment along with geohydro information and produces a series of plots representing the integration of multiple datasets. The outputs plots out of the tool include a 2D plan view, which amalgamates the specified pipeline segment with geoimagery as a background, and also includes elevation profile, horizontal stream plots, vertical stream plots, and total stream plots. It also includes the azimuth plots and the pitch plots. So the example presented here shows the change in bending stream between 2019 and 2015 LI-MU dataset within a geohydro location interacting with dents and the bends. This area of interest also aligns with dig excavation completed in 2017. The assessment of data shown in the top half of the plot indicates a slight horizontal S-band type feature located at the downstream end of the pipe, coinciding with the slack bands. It needs to be confirmed through future LIMU whether this is construction-related or potential area of landslide interaction. The assessment of data as shown in the bottom half of the plot indicates the stream most likely attributed the result of 2017 dig excavation and the subsequent reburial and settlement of the pipe. We can use these plots to identify efficiently and accurately whether pipeline stream is construction-related or an area of land movement event with the potential of more severe consequences in the future. Now I'd like to wrap up this presentation with the benefits and the two future enhancements. This tool is able to assist the operator in making decisions quickly and assist in fitness for service decisions on any further mitigation required. The slides in this presentation represent the tool as it stands today. The future of the tool envisions a web-based tool which can be integrated in Pipeline Operator GIS platform to include a moving windows or imagery above or hovering over the pipeline centerline to include the pipeline features like girth valves and bands and valves and LI features, along with stream plots and geohazard information. This is the bending stream analysis tool, which demonstrates what Stantec can do with the pipeline threads related to outside forces. And now I'd like to ask you, audience, a question and get an idea of your time doing the similar activity in this field so we can better understand each other. The question is, as a proportion of total time to complete and integrate assessments, how much is spent on gathering and compiling your input data? The answers for you to pick are as follows. A, 0%. My data is pre-prepared. I can go ahead do the analysis. And B, 0 to 10%. And C, 10% to 25%. And D, 25 to 50%. Last one, over 50%. So please take your time to participate in this poll. Any feedbacks are highly appreciated. Thank you for your time. And now I turn back to Kim.
Kelly, this tool is so important, and it should be noted that the bending strain analysis tool is supported by a major midstream company that is partnering with Stantec to build out a custom version. Also, as I mentioned in the introduction of this webinar, Stantec has prioritized innovation and digital among its key values. Part of this is to identify and further develop ideas within and to deploy those for optimal use, such as the web platform that Kelly mentioned. Gathering data and discussions of analytics is all around us. Outputs to Power BI, project information management systems with data gathered are just a few of the ways that we can proactively analyze threats and plan for those. So it looks like we have over 50% of data time spent on gathering and compiling input data, so that's significant. I'd like to thank you all for submitting your poll result. And so next up, we're going to hear from Christian Olsen and Brent Cadler to discuss mitigation and use of full or partial scans, allowing for value gain and providing data for use virtually at times when we need to be remote. Hi, Christian.
Thanks, Kim. Today, I'd like to talk about my own experiences as an integrity engineer and the application of popular tools in our industry. We've all seen digital tools used to some degree and with varying levels of success. And a popular example would be the 3D model. Historically, though, 3D models have helped with capital projects, but many of us have had this dream that something similar could be used for the maintenance and turnaround support. And while a 3D model or virtual facility can be built from scans of existing piping, it really needs to offer more than dimensional data to be worth the cost. And so a question I'd like to explore today is this: what features should a 3D virtual facility have that could be carried by a maintenance budget and also provide a lot of value? My talk's going to be a little different than my other colleagues because I'm going to focus on the challenge and then let Brent share some of the solutions and their benefits. So next slide here. Oops. Great, thank you. All right, so let's start with what we currently do. And our integrity work is geared to follow corporately sanctioned risk management programs. That's typically the plan, do, check, and act cycle with continuous improvement. And of course, that's not going to change with digitization. In addition, we have, here we have at each step, there are multiple stakeholder groups working together to upgrade our equipment and reduce operating risks. Of course, that's what we're here for. So that's not going to change with digitization either. Ironically, though, these groups are often drawing from separate sources of information that represent the physical assets a little differently, and they're not always in sync nor up to date. Of course, in engineering work, low confidence in data that typically drives higher levels of conservatism because it has to be safe. Therefore, a lot of work tends to go into resolving unclear and conflicting data, and I believe that's what was reflected in the results of the earlier poll. Of course, after all this work, if we're not careful, a lot of that work that we've just done can get lost as we're repeating through this risk management cycle. Okay, so when it comes to virtual facilities for planning, we really need to do two things well. First is a virtual facility should accurately represent the physical asset in its current state, as we see here. And it should contain both precise dimensional data, but also photorealism. It should be just like being in the field. And finally, whatever software it is should be easy to use and easy to share, easy to install on our machines. Secondly, the facility model should also link these images to corporately supported integrity data, as line numbers, ISOs, PNIDs, and such. And if it's done properly, I feel that this can allow us to do a number of things that would provide immediate cost-saving opportunities. We can plan our inspections in the virtual environment. We can securely collaborate with SMEs wherever they are around the world, looking at the same virtual environment, and updating as required. And finally, we can really do most of our planning in that virtual environment. Ideally, though, that same model that's used for inspection and planning should also be useful for that do, check, and act steps. And this can happen if we're able to create engineering work packages, provide field support during the execution phase. So in other words, it should be a model that's going to allow a piping designer or an engineer to identify an element in the model and then attribute it to a pipe spec or other information, and then quickly generate a 90% review quality ISO. Again, if it is done right, then field work, while it's very important and essential, really becomes an exercise about verification. So or PMI or recent damage mapping, and it's not about taking photos and measuring things or maybe even looking for pipe supports. Also, the designer's notes should be taggable to the equipment, so we kind of create a record of the story of discovery. And it also can be used to facilitate the engineering review and HAZOPs. So this means that we're using a virtual facility as an intuitive framework or a single source of truth upon which we build our integrity program. In addition, this as-built information should be available. So there's what we had now, the as-built, And perhaps there's another scan, but the point is that we want to have a virtual facility that's capable of showing changes over time. Finally, and when required, piping designer, engineer, or inspector should be able to update inspection documents, things like corrosion ISOs, in order to support the next cycle of future integrity work. So with that, I'd like to hand it over to Brent to talk about the state of the art in 3D scanning and the use of scan models for integrity purposes.
Awesome. Thanks, Christian. I'm just going to leave it right here, actually. This is fine. So my name is Brent Cadler, and thanks for introducing the topic, Christian. A lot of the different use cases around the virtual facility and how it can be used. You might be asking, a lot of people have done scanning before, and so what's different now, and what's changed in the last few years? In the last year or so, a whole new generation of scanners is now being launched and being brought into market, and there's some differences that I'd like to go over with you. Some of the key differences is the ability to capture 5 to 10 times more scanning data per day with a surveyor than before. And one of the ways that that's achievable is the scanners are now utilizing artificial intelligence and image recognition with the onboard cameras. And so when you set up the scanner to do a scan in the facility, you have to orient it and coordinate it so that it's inside of the facility in a known location. But when you move it from one location to the next, the scanner knows that it's being moved and it can keep track of where it is. So now you can actually go from one scan point to the next without having to reorient or retrain the device, and you can just start scanning at the next location. That turns into a higher number of scans per day, which turns into a lower cost for doing the scanning. And so like I said, the productivity increases are significant. Scanners are getting to be higher density, so you can get more points per centimeter, and you can start capturing color now too. And this is where the photorealism comes in. It's no longer these really, hard to see black and white scan images. You get these photorealistic pictures of the facility, down to the point of even being able to read tags in some cases, and to actually look at the asset and see what it is. The scanners are getting cheaper and faster all the time, and so not only mobile scanners, but fixed scanners are now becoming practical and usable. And with all the scan data, you're getting more and more points and more data sets, and the power of computers is getting higher, so we're actually able to start merging this data in a much larger data sets than before. So merging these massive data sets, and on the screen is an example of a facility that has hundreds of scans, and this is hundreds of gigabytes worth of data. Traditionally, the scans would be merged, you wouldn't be able to merge a set this large. And if you were able to merge it, it would only be on a powerful workstation with one of your designers, and it would be very difficult to share and collaborate with this data. It would only be for the select few who had those workstations and that customized software. But now with technology, we're able to host this stuff in the cloud, and we're able to share these scan sets over the web using a browser interface. We can merge in the three-dimensional model with the scan, so you can start doing comparisons between the scan and the model, but it's no longer just a design activity. It can be done by anyone on the team. Anyone, whether it be a construction supervisor, facility user, field engineers, or even other engineers in remote working offices. We can all look at and view and consume and collaborate on the same scan data with the same three-dimensional models overlaid. You can really bring that tool set to your team. You can collaborate with your team members. So now that you have the scan data and it's accessible to your team, you can start to annotate and communicate on the scans themselves. And we've been able to use this to replace some of the RFI processes. So you no longer have to have field engineers go to the field to take pictures to then come back to their office, fill out an RFI form and attach all the documents and then send it through an approval chain. They can literally point at an object in the model, tag an engineer, and the RFI can come across instantly without having to have all those other intermediary steps or a field visit. So you can start to measure your RFI turnaround cycles, not from when an RFI was submitted, but from when an RFI was actually discovered and pointed at by the engineer. So that can drastically reduce your RFI turnaround times. Field visits, like we said, with having access to this information, You should be able to do a lot of your work from your desk as far as looking at your integrity isometrics and doing some of your work. And your field visits really change from being a discovery and engineering exercise to being a verification exercise. And so you can do more with fewer visits. So I'd like to kind of finish with a bit of a real world example and something that I'm kind of really proud that we've been able to help one of our clients achieve. So this is a real safety example where one of our client facilities has a fairly hazardous environment with acids. And those acids requires a lot of personal protective equipment before you can enter those areas and perform work. The worker on the screen here, you can see he's got spray shields, masks, goggles, spray suits, double gloves and double boots, as well as a hazardous atmosphere with H2S and gas detection. And the process of getting into and out of this environment takes hours, it takes specialized training. And then when you do leave that environment, because there's the potential for acid to be in that area, you have to go through a decontamination process and everything has to be removed carefully and sanitized and neutralized. It's a lot of risk to the worker, and it's also long-term occupational health and safety implications with this as well. So anything we can do to provide an opportunity for that worker to see the plant and to minimize the required amount of time and trips into that area is a huge help. And that's not just contributing to cost, it's contributing to the health and safety of that worker. So we're really proud to be able to offer these scans and to be able to put them side by side. You can see on the right of the screen, not only the photorealistic pictures of the facility, but you can start overlaying some of your other engineering data onto it. So with that said, I'd like to do a bit of a poll. Which of these use cases for the virtual facility do you feel would be most helpful? Collaboration and planning, replacing site visits, capturing dimensional information for tie points and fabrication, or are you thinking about ideas that we haven't really covered and mentioned? And with that, I'd like to turn it back over to Kim. Thank you.
Thanks, Brent, and thank you, Christian. Thanks for showing us some great examples and reasons why 3D scanning, with or without existing 3D models, can take us virtually to a site that we may not be able to visit physically. Now more than ever, we all need the ability to view data and bring our teams closer together while staying remote. At Stantec, and I'm certain with every company of anyone who is on this call, these remote accessibility initiatives are key. Virtual, augmented, and mixed reality combined with parametric design, eventually these can all talk towards discussions on other innovative ideas. If you are not having these conversations or you have questions, connect with us. We're also talking about all of these great future capabilities, some happening now and some moving forward. All right, so let's take a peek. So replacing site visits looks like just creeped on top of collaboration and planning. So I think that's online, and thanks for taking the time. So far, we've touched on large data gathering, threats, and analytics. We've captured and discussed the visual data to view the reality of our sites or future sites. The importance of data integration and management is what Mark Strickland is going to here to discuss with you. Thanks, Mark.
Thank you, Kim. Welcome everyone to our presentation on data integration. During this talk, we'll discover that we can certainly do more with digital data, as long as the data is strategically integrated. Let me just get this slide. Thank you. Data is increasingly seen as an asset that can be used to promote better business decisions, optimize operations and maintenance, and reduce overall costs. Big data, smart data, historic data. Yep, sure, we live in a world of data, but what is the point if it can't be meaningfully connected? The data value chain defines data as essentially granular or unprocessed information. When data is organized and communicated, in a coherent and meaningful manner, it provides information. The information is then analyzed purposefully to drive insight on which action can be taken. All effective decisions are based on a foundation of integrated and reliable data. Okay. This pipeline repair dig example reflects a common conflict when it comes to pipeline data, although magnitudes can vary greatly. We have a pipeline center line provided by an ILI tool run in yellow that extends from the south, turns east, and then crosses the railway right-of-way as shown in pink. Our target girth weld is approximately 16 meters east of the right-of-way, as determined by ILI target coordinates. All looks good and seems to be pretty straightforward repair dig. However, what happens when I introduce another data set from a different source? The orange centerline is based on a depth of cover survey conducted a few years previously, and it deflects from the ILI trajectory prior to the crossing. A closer inspection highlights an east-west difference by approximately 20 meters at the bend. This data overlay suddenly calls into question the target girth weld position and introduces a variety of possible execution strategies that will range in both time and budget. We can either rely solely on the ILI and dig 16 meters east of the right of way, or we can consider the depth cover survey center line as accurate and plan for a dig 4 meters within the right of way. The most robust solution is to evaluate and combine information from both sources to pinpoint the most probable location. Now, tactically, this is a basic example that incorporates only 2 conflicting data sets and may have a small number of solutions. However, if you scale up an example such as this to take into consideration the immense volumes of data within a pipeline data management system, you can start to imagine the impact on the decision process. As we all know, data comes from a wide variety of sources using different collection methods, data types, formats, and quality standards. Data integration is the primary step towards transforming data into meaningful and valuable information. It is the process of combining data from different sources into a single unified structure. It requires making inputs consistent, such as units of measure, data types, domains, etc., and also centralizes the data into a single source of truth that provides a more rigorous data management structure for collaboration, interaction, and communication. ETL, or extract, transform, and load tools are generally used to convert and integrate data from varying sources. So after all these years and advancements in technology, garbage in is still equal to garbage out. Automation and machine learning, AI, etc., they will not fill the void left by poor data alignment. On the contrary, it can actually lead to corrupt analysis and misdirection. So how do we ensure the data is capable of supporting business decisions and has the required granularity when needed? We inspect the data through a series of critical lenses. Business logic or use case provides the functionality of the data. It defines what data is needed and why. Spatial dimension is used to define the locational characteristics of data and how they are related to each other positionally. And finally, data governance provides the strategies for data structure, traceability, completeness, and currency. Just a quick note to remind viewers that it's never too late to integrate your data cohesively. The data integration principles are completely scalable, meaning that they can be introduced prior to building a pipeline data management system or to enhance an existing system. They can even be deployed at the project level. So for the final thoughts, like data can be a valuable asset. Data integration lends to higher order analytics from which greater knowledge is attained, producing much more efficient and reliable actions. Thank you all for your time. Over to you, Kim.
Great job, Mark. You've highlighted how much data is an asset and how detrimental data loss is. With the digital age moving towards, or in many cases already in, BI and analytics, successes we've had with moving the data to the field, like with our mTools application or the GIS datasets we are using to map heat grids, that can't happen without data integration. And now I'm pleased to welcome James to summarize the various topics we've covered in our presentation.
Thanks, Kim. Increasing reliance on digital solutions is driving change in how we do our work. Each of the solutions presented today relies on a specific workflow to extract value from the data lifecycle. In order, data comes into existence when we measure a quantity or sense a condition. That data is then combined with data from other sources, ultimately to enable the required analysis or design. Traditionally, this workflow starts when we need data for an analysis. Let's examine the solutions our panelists shared to see when pre-planning the data workflow is beneficial. First off, Stantec's remote sensing solution that monitors for encroachment and leaks on the right-of-way combines all the steps of the data lifecycle into one platform. As Grant described, PipeWatch integrates the satellite measurements of vegetation with the pipeline right-of-way to feed the analytics of change detection. This data workflow is clearly planned, put into place, and then run every day to achieve the remote sensing objectives. Moving on to the Bending Strain Assessment Tool, or BSAT, it relies on a different workflow. Kelly showed us how the BSAT starts with a number of offline data sources, including strain measurements from inline inspections and Stantec's geotechnical survey findings. The BSAT integrates these data sets to enable the critical analysis of detection and assessment for slope instability. One of the inherent challenges that this data workflow addresses is harmonization of ILI data sources that are gathered to differing standards, potentially 5 to 15 years prior to the analysis. This data workflow is planned and programmed into the BSAT to enable management of the geohazard within an integrity timeline. In contrast to the BSAT, which encompasses data integration, the virtual facility solution is built around existing coordinate transformation technology. Christian and Brent showed us how recent advances in Stantec's laser scanning provides base data that can be further augmented with design using 3D CAD. Hosted for remote users, the virtual facility is capable of supporting online walkthroughs as well as design and operability reviews from anywhere with an internet connection. In order to maximize value of the virtual facility, for example, to reduce or eliminate the need for physical site visits, the scanning and integration workflow needs to be conducted beforehand. Moving back to pipelines, in our last example, Mark walked us through a robust and broadly applicable data workflow suitable for managing linear assets over a service life of 70 or more years. Data gathered at different times in the life of a pipeline is inevitably also gathered to differing standards corresponding to the point in time when each survey, as-built, and inline inspection was completed. Coming at the present time, data integration for a 50 or 70-year-old pipeline is an afterthought and carries a heavy reliance on quality assurance, such as data governance and geomatics to correct for inaccuracies in ILI mapping. At the end of the day, regardless of the point in time when each data workflow starts, the goal is to build a foundation to support analytics and other types of knowledge synthesis, including artificial intelligence, upon which our industry can reliably base decisions for safety and commerce. I will now turn it back to Kim.
Thanks, James. So we do have a couple questions already. And before we jump into the question, I want to thank everybody for taking the time to join us. We want you guys to ask us questions. And if you do have any questions that pop up afterwards, we actually will be sending out an email with everybody on the panel, each of their contact information. So please reach out to each and any of us if you would like more information or you have questions further. So I'm just going to I hope I'm saying your name right, Afolabi, actually has two questions. So I'm going to ask Kelly to respond. So question one for you, Kelly, where multiple IMU data is available and strain changes are determined, how much change in bending strain in unexpected areas is large enough to trigger pipe excavation?
Okay, thank you for the question. So when we evaluate multiple IMUs and to detect the change in bending strain over years, the minimum filtering thresholds can be as low as 0.02% after those features are identified, and then those features need to be classified according to and the source and the type and the activity, by considering the elevation change detection from LiDAR data and construction or maintenance activity records. And then the next step, an engineer assessment will be conducted to determine the fitness for service of pipeline segment within that identified IMU features. So then along with those assessments, we can prioritize the corresponding mitigation actions. So for example, active IMU feature, which continues to deform over 2 or more IMU runs, so we consider for immediate engineering assessment or risk control measure. So at these points, there's no fixed amount, the value of strain, but we will come up with a solution by considering multiple records. Thank you.
Thanks, Kelly. And while you're up, I'm going to ask you the second question, also from Afolabi. Is the bending strain analysis on a fine enough scale to be used to manage CSCC on pipelines?
Oh, I would say yes, because the land movement is one of the sources to cause SCC.
Thank you, Kelly.
Mm-hmm.
All right, so we have a few questions coming in from Shane Goosney. Hi, Shane. So first question, Christian Brent, how are you doing remote collaboration with these large data sets?
Hey.
Hi.
I guess I'll jump in and take that one. So right now, the biggest way we're doing remote collaboration is, like I'd mentioned, with using the scan data to reduce the number of field visits using the scanned facility to help with the creation of isometrics for integrity purposes, and then using the scan data and the model data combined to do RFIs and to improve the RFI process. So you can actually start identifying and communicating on RFIs before you actually get to the field with a camera, for example. There's a lot of other use cases that we're looking at and developing, but those are the big hitters right now.
Okay.
Anything you'd like to add, Christian?
You're on mute, Christian.
You know, you're right. I mean, everybody's situation is a little bit different. And I think that's part of the benefit is we can be quite flexible in how we collaborate.
Okay, thanks. And Brent, with respect to the model RFIs, how are you processing, storing the documentation for these items?
Typically, because this is a fairly new capability, a lot of the information gets duplicated into our traditional RFI systems so that all of the traditional stakeholders don't get bypassed. But in addition to having everything go through the traditional methods, a lot of it can get stored within the model. So a lot of the communications back and forth gets tracked as a conversation, and you can attach documentation as an attachment to the annotations within the model. So the honest answer is that there's a bit of duplication just because we're not ready to fully leap into the deep end with the virtual facility, but the capability is there and it's being used.
Thank you, guys. And question again from Shane. Thank you, Shane, for being so interactive. This question is for Mark Strickland. So question for Mark, do you use a set data validation workflow, or do you build it based on the situation from available tools?
Thanks, Kim. Yeah, I think we have, there's a variety of options. Stantec follows a general protocol for data integration. There's a little bit of flexibility built in just depending on the data sources and the different types of data that will form the inputs for a particular database management system. So yeah, Stantec does have, you know, some set tools and workflows, but there is some flexibility and variability built into those just because the inputs and the target the target structure or database for a particular client may differ. Thank you.
Thank you. And we have a question for Grant. Both aerial patrols and satellites have limitations. Can the PipeWatch remote sensing solution detect pooling of hydrocarbons on the ground?
Yes, thanks, Kim. Anytime, any situation where there are high hydrocarbons on the ground, you know, in liquid format, that's gonna set off a huge red flag. Any sort of liquids have a very, very low score in our vegetation health indices. So yes, if those hydrocarbons are present, if they are pooling on the surface, they would be detected fairly easily. Thanks.
Thank you. And we're at 1 minute to the end of the hour. So again, I want to thank everybody for attending this webinar. It's a lot of data and information for everyone to process. Again, any questions, please feel free to come back to us and ask. Yes, there will be a recording available sent out to all attendees, as well as we will put some postings up on stantec.com. Likely we'll send out some social media links to access this webinar afterwards. So thanks again for attending and have a great day.